Hi guys. In this video we will focus on the exact carbonyl position in the IR. The carbonyl position can vary depending on the exact carbonyl containing functional group. And it's very useful to understand the variation that we can see with the different carbonyl groups. Of course, there are carboxylic acid derivatives. Most of them all have a carbonyl, whether it's a carboxylic acid or ester or amide, those being the most common. Of course, a nitrile does not have a carbonyl, so it's not relevant to this discussion. But also in this discussion, we'll look at aldehydes and ketones, and how the carbonyl absorbance or stretch varies for them. Okay, there's a very important resonance structure for the carbonyl group. That's the polarization of the carbonyl. We have a dipole, but we can also just show a resonance structure where we can just move electrons up towards the electron demanding or electronegative oxygen, and we can show a alternative Lewis structure such as this, which we call a resonance structure. And it turns out the more that this resonance structure contributes to the resonance hybrid, the weaker the C double bond O is. The more this contributes, the weaker the carbonyl bond is. That is, look at this. The more this contributes to the hybrid, the more single bond character you have versus double bond character. And the more single bond character you have, the weaker the bonding is going to be between the carbon and oxygen, because a single bond is weaker than a double bond. Now we should also know that the weaker the bonding is between the C and the O, the lower the wave number in the IR. Because we learned in Organic 1 when we first introduced IR that peak position is based on two main things: mass of the atoms, but in this discussion it's carbon and oxygen in all cases. We're dealing with carbonyl. The difference here is going to be the second important thing, which is bond strength. The stronger the bond between the two atoms, the faster it will the bond will vibrate, such as by a stretch. Stronger the bond, higher frequency of that vibration. Higher frequency would equate to higher or longer wave number. On the flip side, the weaker the bonding is, the lower the wave number. Ultimately, the more this contributes, the more this resonance structure contributes, the weaker the bonding is, and the lower the carbonyl stretch will be in the IR. Now we can say that another way with these diagrams here. Or not really saying another way, but let's look at how groups can affect this. If we have an electron donating group bonded to the carbonyl, that's going to make this resonance structure contribute more. Because, think about it, this resonance structure has a positive on the carbon. What's going to help facilitate forming a positive on this carbon? An electron donating group. On the other hand, if we have an electron withdrawing group, that's not going to facilitate a positive being formed on this carbon. That's going to hinder it. Thus, that will hinder the contribution of this resonance structure. And thus, this resonance structure will contribute less when there's an electron withdrawing group. Okay, so you need to get these two straight. Ultimately, we need to determine, when we look at groups, are they electron donating or withdrawing? And very often we'll be comparing them as opposed to making absolute considerations. So, let's look at some acid derivatives here. Acid chloride. It turns out acid chlorides have a very high carbonyl position in the IR, approximately 1800. If you remember a typical carbonyl region, I would typically say about 1650 to 1750 maybe. 1650, 1740, something like that. 1800 is a high carbonyl. Why? Because the chlorine is a net withdrawing group. That's analogous to this here. And with a withdrawing group there, this resonance structure is going to contribute less because the molecule doesn't want to develop a lot of partial positive here if there's a chlorine here withdrawing. So with the chlorine, you actually get more contribution for the full double bonded resonance structure, and this effectively makes the bonding between the C and the O stronger because there's more double bond character. Stronger bonding between the C and the O leads to a higher wave number. We can compare that to esters. Now, esters have sort of a mid-range to slightly high wave number. The fact that the wave number is lower tells us that this contributes more. Well, why? Because the oxygen is actually a net donator. It can donate by resonance. Yes, it withdraws inductively. But the more major effect is the donation by resonance. It's actually a mixture here. The difference is, yes, the chlorine can donate by resonance as well, but with halogen, the withdrawing is the major effect. But with oxygen, the major effect is the resonance donation. So we have more of the donating, and it makes the single bond resonance structure contribute more to the actual resonance hybrid. This leads to a lowering of the wave number for the carbonyl stretch compared to the acid chloride. If we look at amides, which have nitrogen, nitrogen donates even more. Substantial resonance donation. And if you remember, we actually looked at the resonance of amides in lecture, and I actually showed you a proton NMR that is evidence of resonance. Substantial donation here that really helps the single bonded resonance structure. We can get to that. We can show the resonance structure, the polarized resonance structure. And then we can say, well, how much is this going to contribute? Well, it contributes a good bit because this cation is stabilized by resonance. I'll come back this way, and we can get to this resonance structure. Again, though, still we see there's single bond character here that comes from this resonance structure. And together we have even more contribution towards single bond between the C and the O compared to double bond. So nitrogen likes to donate a good bit because nitrogen doesn't mind becoming positive. We've said these things a number of times. Stronger donator by resonance. Okay, so the amide carbonyl is even lower. And this is typically a low-range carbonyl. And these values here can be even lower. A little surprised that I listed that. That may be what's in a textbook, but a lot of times amides will be like 1630 or 1640. Particularly disubstituted amides, where if you start putting alkyl groups on this nitrogen, the nitrogen is even more willing to take on plus because it has donation from sp3 carbons. Okay, take home here. Acid chlorides typically have high carbonyls. Amides typically have low carbonyls. Esters are intermediate between the two. Okay, what about aldehydes and ketones? Well, let's look at them relatively. Let's compare them. That's just H. We'll consider this just the same here. The difference H versus an R group. Typically sp3 carbon, it's going to donate inductively versus nothing with the H, no electronic effect to consider there. Donation, well, if we have a donating group, it's going to contribute more because it helps stabilize the plus that develops here. If it contributes more, we would expect a lower value for the carbonyl, and indeed we do. Ketones typically have lower carbonyl stretches compared to aldehydes. Now, you got to be careful though. Yes, that's the take home there. But look at this aldehyde. This is an aldehyde. The carbonyl is 1699. A lot of times I'll see a student get an IR and they'll say, look, carbonyl 1699 ketone. Well, there could be other things going on. So let's look down here. Regular aldehyde, this molecule about 1739 for the carbonyl stretch. This one 1699. Why? In this case, it has to do with the conjugation with the alkene. I'm showing that here. I've sort of flipped the molecule around. If we show our polarized resonance structure, we can then stabilize that further by resonance from the alkene. Resonance donation stabilizes it even further, and it makes the polarized resonance structure contribute even more. You're getting more and more away from the sort of full double bond structure. Ultimately, we call this a conjugated carbonyl. This pi bond is conjugated with this pi bond. Conjugated carbonyls have lower carbonyl peaks in the IR compared to non-conjugated carbonyls. We also see that with like benzaldehyde, because the carbonyl is conjugated with the pi system of the aromatic ring. And that lowers the carbonyl. All right. Take home message. Conjugation lowers the carbonyl. Okay, let's look at some examples of acid derivative IRs. First one here is a carboxylic acid. Okay. Key feature here, and a lot of this is review from Organic 1. But this gives us a chance to review our IR. In addition to the sort of what may be a little bit new information with the positioning of the carbonyl stretch. So the carboxylic acid has your broad OH, right? See that broad absorbance for the carboxylic acid? The broadness is largely due to the acidic nature and very strong hydrogen bonding. between different molecules, which leads to that broadness. Then we have our carbonyl. The exact position is 1716. Sort of like an ester, because I didn't show carboxylic acid here. Sort of like an ester. But why is it not 1730, 1750? Well, I was going to say because it's conjugated, but it's not. Perhaps I should have showed the carboxylic acid over here. Carboxylic acid, although I don't see this a lot, I believe the carboxylic acid has a little bit lower carbonyl than an ester. Not sure if I can explain that. I'm not sure I really thought about that much before. Because usually the main thing with the carboxylic acid is you see this broad OH. But it looks like the carbonyl is sort of just a kind of a typical carbonyl region. So I put over here on the side, it got hole punched, but sort of the main thing, key feature, broad OH. Let's look at acid chloride. What do we expect? High carbonyl. Indeed, here's your carbonyl, and the exact position is, well, exactly 1800. Indeed, high carbonyl. Fingerprint. What do we have here? sp3ch, which is all we have here. And what is this here? It's likely an overtone of the carbonyl. Carbonyls, because it's such a strong absorbance, it's very likely to give an overtone. You can tell it's an overtone because typically it's double minus a touch. Double 1800 would be 3600 minus a touch. I think that's a 5. That's a 3580, which is double 1800 minus a touch. Overtone comes from vibrational levels. Your vibrational levels, as you come up, they get closer and closer. And basically these vibrational levels, you can excite the bond to a higher vibrational level by putting in some energy. And usually a single excitation is what we're looking at, what most of our peaks come from. But sometimes you can excite it to the second level. And this is, the energy here is delta E times 2 minus a touch. Because it turns out as you go up in energy levels, they get a little bit closer and closer. And of course, a higher frequency is going to equate to higher energy light that did this transition and was absorbed to give you this transition, and thus we plotted the absorbance there. So an overtone. Strong carbonyls often give an overtone. So, high carbonyl, sp3ch, anhydride. This is the anhydride of benzoic acid. Now, an anhydride has 2 carbonyls, and indeed we see 2 carbonyls in the IR. These are 1726 and 1788. Indeed, one of them tends to be sort of mid-range, the other one tends to be a little high. I'm not going to get into the exact positioning there, why that is. 2 carbonyls I will say this. The reason you get two peaks here is not because exactly there's two carbonyls. The entire molecule gives two peaks. You actually have what's called a symmetric stretch, where both of the carbonyls are sort of stretching like this, and that leads to one absorbance. You also have another stretch called an asymmetric stretch, where the carbonyls are stretching like this, and that leads to the second absorbance. So that's really why there's two carbonyls. Of course, this molecule has no sp3CH, it's only sp2CH. If we draw a line here at 3000, we can see that the absorbance here is above 3000. We could also look at the numbers here, and you see 3010, the next number 19 something, although we do have some little peaks here, which could be a little bit misleading. You could be like, are those peaks? Well, they certainly could be. But for this molecule, we do not expect any peaks below 3000. Possible overtones here, although that's quite weak. Basically, two carbonyls and sp2CH. Here we have an ester. Which we expect a mid-range carbonyl, although it is conjugated. The carbonyl is conjugated over here in addition to the oxygen. So we might expect it a little bit lower than sort of mid-range typical. We expected sort of mid-range to a touch high, 1730, 1750. This carbonyl is 1719, looks like. So it's a little lower than what was stated on the previous page because it's conjugated. Conjugated over here on the other side. Then we have both sp3CH and sp2CH, and so we have at the magic 3000 line so we have both types of CH there. Perhaps an overtone. What's double that? 34, 38. Really not giving peaks here. That does seem to be about 34. I don't know. Hard to tell that's an overtone or not. We would need the exact peak. If it's not an overtone, I don't know what it is, because we don't expect to see it have an NH or OH in this molecule. Okay, so here we said normal carbonyl, although it is conjugated, so it lowers it from the sort of standard value. The other thing is, typically we don't look in the fingerprint region, but with esters, the CO bond, the C single bond O, is often fairly strong in the fingerprint region at about 1200 to 1300. And usually we can pick that out. See that peak there? It's kind of a little bit broad there. Probably that single bond CO. If we look back, for example, acid chloride, see here in the sort of the 1200-1300 how there's no strong peak? Well, to me that doesn't look like an ester. And actually up here, didn't mention it here, but the CO in the carboxylic acid, see this strong peak here at about 1300? It could very well be the CO single bond, where again the acid chloride doesn't have that. So that's one time we can look down into the fingerprint region and maybe get some additional information. Okay, here we have a primary amide. We expect a low carbonyl. We also have NHs, and we expect 2 NH stretches. And so here's your 2 NH stretches. Low carbonyl, which is about 16, what is that, 16, it's coming all the way down to about here, 50, 40, 30, 20, 10. It's coming all kind of down to about 5. I think it's this peak here. 1661. So we see that's a fairly low carbonyl. We will see even lower though. sp3ch, a little bit weak here. Little bit weak. Could be sort of covered up by this absorbance from the NHs that's sort of tailing off. Now the compound below is a secondary amide. We only expect 1 NH. The CH peaks are more prevalent, and indeed we have both types because we have this sp3ch here. We do have some peaks above 3000, you know, like it right here in this range. And then our low carbonyl, which is probably, what is that, 1639 probably? And so it's even lower than the primary amide. If you think about it, this methyl group donating, sp3 carbon is a donator. Again, I mentioned this earlier, but if this nitrogen has a donator on it, then this nitrogen is going to be even more willing to take on positive because it's got a rich friend donating electron density towards it. And that's going to lower the carbonyl even more. And the next example is a tertiary amide. No NHs. That's a little odd. What is that? Could be a little water if this is a real spectrum. We don't expect any NH, and it certainly doesn't look like the NHs we had over here. Strong stretches for the NHs. Again, we have both types of CH in terms of our more typical sp3 and sp2. Of course, the third type would be a SPCH, but that would require an alkyne. Low carbonyl, 16, what is that, 20? 25? Is that a 5 or a 6? I think it's a 6. 1626. That's quite low. That's probably about the lowest you'll ever see a carbonyl. When I mean low, I'm talking about wave number. You have this nitrogen has two rich friends, so it's very willing to take on a positive charge by donating towards the carbonyl. And again, donation toward the carbonyl is going to effectively weaken the carbonyl, and that's going to lower the value in the IR. Okay. Now, we should point out nitriles. It's an acid derivative, although it doesn't contain a carbonyl. And of course, your nitrile is typically about 2200. This one in particular is 2230. If you remember from Organic 1, I mentioned that nitriles are typically just above 2200, where your carbon-carbon triple bond is often just below 2200. But that can vary. And then we only expect sp2CH. And so it looks like this is your sp2CH. Lots of, I don't know if that's noise or what, aromatic signature, but lots of stuff here. It's a little bit odd. So much going through there. Fingerprint. By the way, you remember the CO in the fingerprint? You see how there's at 12 to 13, there's really no CO. Of course, there's no strong peak here either for the CO, because these molecules don't have that. Okay, this handout does not include aldehydes and ketones. I just included it on the front page just for comparison to the acid derivatives, the amides, esters, etc. So we can take this idea of donation, withdrawing, etc., and apply it to aldehydes and ketones and understand why the ketone would be a lower carbonyl. But I also then showed you the conjugation. And I only showed you conjugated aldehydes or ketones here, but you can have conjugated other things. For example, we did see one where we had a conjugated ester, and the carbonyl was lower than sort of the non-conjugated value, which would be more like 1740 or so. Okay, so that's some of the IR of acid derivatives. It gives us a chance to review our IR. And you'll find problems in the workbook that are just IR. And for test 3, that's typically what I cover or ask you to be able to do. And then we'll go back to comprehensive spec problem for test 4. Okay guys, that's a little bit of IR. See you soon.